We normally use rectangular coordinate system to define the points or coordinate of the particular vector. So in this rectangular coordinate system, the basic unit vectors will be used to define the points or the coordinate of the vector. It is the directions of the basis vectors that establish the positive directions, and it is the length of the basis vector that establish the spacing between the individual points on the axis. So based on the basis of this two-dimensional space, we can define the coordinate of the point or a vector. Similarly, in a non-rectangular coordinate system, to define the coordinate of this point P, C, and D, so the unit vectors or the basic vector will be the basis vector will be along these directions with this length and along this direction with this length. So based on these two examples, we can see that the coordinate of a point or a vector is actually depends on the basis. So we define the coordinates based on the basis of the system. Let's look at this example, the standard basis for a two-dimensional space. So the basis for this R2 is actually 1, 0, and 0, 1 coordinate, or the unit vectors here. Reason being, these two are known as the bases because they are linearly independent, because you couldn't express u1 in the form of u2, or you couldn't express u2 in the form of u1, and because combinations of these two u1 and u2 can give you any points or any coordinates on the two-dimensional space here. So you try to recall back from the previous lesson that if these two are considered as a basis, they must fulfill two conditions, which is the span and linear independence. You try to use these two as the vectors, and you prove that these two vectors actually span the whole R2 and they are linearly independent. So the coordinate of P, let's say coordinate of P is 2 and 4, which is actually derived from the combinations of 2 unit vector 1 plus 4 unit vector 2, and the coordinate of Q 4 and 3 is actually a combination of 4 unit vector 1 and 3 unit vector 2. Similarly for R, where the coordinate system is -2 and 3, and S, the coordinate system is 1 and -2. So this coordinate system is actually derived from the combinations of those bases here. Then we have the standard basis for R3, which is considered as the 1, 0, 0, 0, 1, 0, 0, 0, 1, which is actually corresponding to your X, Y, Z, or I, J, K in the three-dimensional space system. And the standard basis for a matrix of a size 2 by 2 is actually 4. So the first one is 1, 0, 0, 0, the second one is 0, 1, 0, 0, and following on. So these 4 matrices is actually the basis for the matrix of size 2 by 2, because you can get any 2 by 2 matrices just by combining these 4 matrices together. For example, this is the matrix M. 2, -1, 0, and 0.5 is actually the combinations from 2 multiplied with the first basis matrix, and plus the -1 multiplied with the second matrix basis, and the third one, the fourth one, and it is these combinations of the 4 matrices you will get the M matrix here. And we write the coordinate of the matrix. M means that M in the brackets of S means that this is the coordinate system of the matrix is in this list form: 2, -1, 0, and half. But in reality, we normally don't deal with the coordinate of a matrix, because the coordinate system that we have used most of the time is referred to the 3 space and 2 space, and it is very rare for us to use the coordinate system of a matrix in any calculation. Now, since that the matrix of 2 by 2 you need to have 4 bases here, how about the basis for the matrix of 3 by 3? The next one is the standard basis for polynomial equations of raised to the power of n order. So let's consider this case, the third order of polynomial. You know that from the previous lessons that the basis for the polynomial of third order is x0, x1, x squared, and x cubed. So these 4 are the basis for the polynomial of third order, because using these 4 bases you can create any polynomial as long as the highest power is raised to the power 3. So for example, this is the Q polynomial with the functions with the equations here: 1 minus x plus 1 over 3x squared minus 2x cubed. So it's actually a combination of 1 multiplied with the Q1, the first basis, and plus the negative 1 Q2, the second basis, plus 1 over 3 multiplied with the third basis and negative 2 with the fourth basis. And we can write it in this form. The coordinate of these polynomial equations is actually 1 minus 1, 1 over 3, and negative 2. But similar with the previous case, the matrix, is very rare for us to use the coordinate system of a polynomial in our calculation. Now let's look at one of the example here. Assume that you have been given three vectors v1, v2, and v3 here, which are the bases for the R3, the three-dimensional space. So you have been asked to find the coordinate vector of v. 5, negative 1, 9 relative to the basis consists of the v1, v2, v3. So we can write it in this way. We know that the coordinate vector is actually the formations from the combinations of k1, v1, k2, v2, k3, v3. So we substitute everything inside these equations. What we need to do is to find out what is the k1, k2, k3, such that we can get the coordinate for these combinations. So you put it into this system of linear equations and you solve it using the row operations. At the end, you will find out that the value for k1 is 1, k2 is negative 1, and k3 is 2. So this v is actually a combination of one portion of v1 plus the negative multiplied with the second basis plus 2 multiplied with the third basis. So in conclusion, the coordinate system for this vector is actually 1, minus 1, and 2. So try to link it back with the previous lesson here. The coordinate of a point is actually a combination of the bases here. And since v1, v2, v3 are the bases, so the scalar multiplications in front of the bases are actually for the coordinate system. Then the second example is to find the vector v in R3, the three-dimensional space whose coordinate vector relative to S is vs negative 1, 3, and 2. So this is the coordinate point of the given vector, and you have been asked to find out the vectors of the v here. So we know that the v is a combination of negative 1 portions of v1, the first basis, and 3 multiplied with the second basis, v2, and 2 multiplied with the third basis, v3. So you just need to substitute everything here and you'll get the answer for v, which is equivalent to 11, 31, and 7. So this is the vector of v. And the previous example solution here is actually to find out the coordinate system. And in this case is to find out the vector.